Okay. Now, with the problem we finished off with yesterday, where we had the over 100 different types, or the 100 different possible rational solutions, what I would have done with that function next, and what I've done to solve that to find the values, is I would have graphed it. I would have graphed it to see where each one of the times it crossed the line, and eliminated any out of those possibilities that didn't fit, and gone from there. So that's what I would have done and worked it out using the graph and trying to figure out what are they close to. Now, conjugate pairs. Complex zeros occur in conjugate pairs. Let there be a polynomial function with real coefficients, this, where if a plus bi, where b is not 0, is a 0 the function, then the conjugate a minus bi is also a 0. We can't have one complex without its pair. It's got to come in pairs. Because the pairs, when they multiply together, the I terms will cancel out. They have to come together. For instance, the result applies to the function f of x equals x squared plus 1, but not to the function g of x equals x minus I, because x minus I is just a1. X squared plus 1 is x plus I and x minus I. We have those two together. So whenever time we see that we have any imaginary terms as a 0, their complex conjugate is also 1. Because if I have positive 3i, I also have to have negative 3i. If 3i is a 0, then the polynomial is said to have real coefficients, this here. So negative 3i is a conjugate, so we have negative 1, 3i, and negative 3i as our 4. As our 4 factors. Now we can rewrite them as this here. So essentially, we set them equal to x. So x is equal to negative 1. X is equal to negative 1. X is equal to 3i, and x is equal to negative 3i. Here we'd add 1 to both sides, and I get x plus 1 equals, because those are the same. Here I would subtract 3i. And lastly, I would add 3i. And then we can rewrite them as a multiplication, because that's how we kind of broke it down when solving. So then we can put them all back together and get this here. Well, from there, if we want to multiply it out, we'll just say a is 1. So we get x squared plus x plus 1 if we do the distributive property on the first step. Here we get x times x, which is x squared, plus 3xi, minus 3xi, minus 9i squared. Well, I squared I know is negative 1. So what I do is I mark I squared out and change the sign. Since it was minus 9, it's now plus 9. Questions on this here? Well, those two cancel out. Here I've got x squared plus 2x plus 1. Here I've got x squared plus 9. We can distribute x squared times x squared is x to the 4th. X squared times 2x is 2x cubed. X squared times x is plus x squared. Do the same thing with 9 and get plus 9x squared plus 18x plus 9. Interesting enough for this here, we only have one set of like terms. X squared plus 18x plus 9. And this is one of the possible polynomial functions that would define these zeros. What did I do from the original one to get to the second one? What changed? not squared. I doubled it. I multiplied everything by 2. 1 became 2, 2 became 4, 10 became 20, 18 became 36, and 9 became 18, yes? Did I change those zeros? Well, no, it's the same zeros, yes? It's just now A, where we had A here, is now 2. I've changed everything else about the function except where it crosses the x-axis. Or, in these two cases, doesn't. But it still has those points. It still has those solutions. I've just increased everything by a factor of 2. What else could I do it by? 4, 5, 6, 7, 8, 9, 10. Any number, yes, positive or negative. And would I get a different equation? Would they look different? Well, yeah. Are the solutions changed? No. Then using the linear factors, the theorem can be written as this. So it's a way to write it. I just picked the value of a to be 1 for the first one. Then for the second one, I picked it to be 2. And we could have picked 2/3. I mean, it doesn't matter. It can be whatever we want it to be. Now, for most part, I pick 1. Most classes, most professors will pick 1. Less to deal with. Less to work with. This here, we get these here. So you obtain the following 4th degree polynomial function, which we got, yes? And then we found one where a is 2. So that's it. That's all we're doing. Does this make sense? So it should bring back memories from chapter 1, where we talked about we didn't have complex terms. We had some radical terms. We didn't have complex. It's the same thing, where x is equal to 2, 3, and 4. Find the least, or find a version of the polynomial function when multiplied out, expanded out. Same thing here. Same thing here. Factoring. Linear factorization shows that you can rewrite any nth degree polynomial as a product of n linear factors. However, the results include the possibility that some of the values of C are complex. Because as we just saw, x squared plus 9 was x plus 3i and x minus 3i. So it's not always that they're going to be real. We might have some complex. And that'll include the fact that C is not going to be a term. C does not have to be a term. X. Here, C is 2. It's a complex number. Did y'all see that there? Because C, when we denote most variables, especially uppercase or lowercase. So I'm going to stop the video. But that's it. This is our C, because we can have more than one term. Every factor of the polynomial function, every polynomial of degree n greater than 0 with real coefficients can be written as the product of linear and quadratic factors with real coefficients where the quadratic factors have no real zeros. So instead of writing some, like the x squared plus 9, we don't necessarily have to write it as x plus 3i and x minus 3i factors. We can leave it as x squared plus 9. We can leave it as that. Because we can also write it as quadratic factors. Anything that won't simplify to real terms or real solutions, we can leave as a quadratic also. For example, x squared plus 1 is equal to x minus I times x plus I. On the other hand, x squared minus 2 is x minus the square root of 2 plus the square root of 2. Those also have conjugates, irrational conjugates, but they can be reduced. Find all the real zeros for this, given that this is a 0. Given that this is a 0. So I also know that 1 minus 3i is a 0. So I know that both of these are zeros. There are ways to use synthetic division to do this. There are ways to do that. I'm not going to do that. Because what we're saying is x is equal to 1 plus 3i, yes? I'm also saying x is equal to 1 minus 3i, yes? If I move these over, so I would subtract 1 for this one here and then subtract 3i. Yep. We good with that there? Here, I would subtract 1, but I would add 3i. I am going to multiply these together because this is what my main goal is. I'm going to multiply those back together and get a polynomial function. Because x times x is going to be x squared. X times negative 1 is negative x plus 3xi. Then we'll do the same thing with negative 1. You get negative x plus 1 minus 3i. And lastly, we'll get minus 3xi plus 3i minus 9i squared. Well, the negative 9i squared is just the same as plus 9, yes? So x squared is the only x squared term. Negative x, and that's it. So we have minus 2x. 3xi and negative 3xi cancel out. Negative 3i plus 3i. They cancel out. 1 plus 9 is plus 10. So we did all of this here really to say that this here is one of our polynomial factors. I'm going to erase this here just so I have the room. So we have this here. I'm going to use it to solve for the rest. Because we have a degree 4, yes? If I can decrease it by 2, I will have a quadratic, and we know how to solve quadratic formula. We're going to use long division. X to the fourth minus 3x cubed plus 6x squared plus 2x minus 60. What times x squared gives me x to the fourth? X squared, just x squared. X squared times x squared is x to the fourth. We have minus 2x cubed plus 10x squared. And then we would subtract, and those two would cancel like we wanted, yes? It'd be negative because a negative make a positive. Negative 3 plus 2 is negative 1. 6 minus 10 would be negative 4 x squared. Bring down the 2x. Then we'd have what? Minus x, because negative x times x squared gives us negative x cubed, yes? Negative x cubed. Negative x times negative 2x would be plus 2x squared minus. Any questions on any of this here? And then we would subtract. The first two would cancel out. Negative 4 minus 2 would be negative 6x squared. Negative and negative make a positive, so we have plus 12x minus 60. Last one's going to be minus 6. Because what times x squared gives me negative 6x squared? Negative 6. Because we said that these two are factors, yes? Factors will always leave a remainder of 0, so I know it's 0. So the equation that we got was x squared minus x minus 6. Yes? So we know that this is a solution. We knew that this is a solution. Now we're just looking for the other two. At this point here, I can use the quadratic formula. Negative b, so negative 1 is just 1. Plus or minus the square root of b squared minus 4 times a times c all over 2a. So we can type everything that's inside the square root into the calculator. Well, 1 squared is 1. Negative 4 times negative 6 is positive 24. So we should get 25. You can check me on that and make sure I got that right. So if I got that right, it should be the square root of 25. I see. It's yep. One plus 5 over 2, and 1 minus 5 over 2. Well, 1 plus 5 is? Divided by 2 is? 1 minus 5 is negative. Divided by 2 is? One, two, three, 4. I got all 4. So a lot of the times, if they tell us one of these solutions is imaginary, I would multiply it, find its conjugate, and do the multiplication like we did here at the start, and then use its combination, that quadratic, in long division to simplify from there. Because trying to do it with synthetic division with that complex number is not always the easiest thing to do. Now here it worked out that if I had to graph this thing, it had given me the other two answers, because they're the values for which, the values of x for which y is 0, or what they're the value of x that make the function 0. So if I graphed it, I'd just seen where's y 0. Oh, it's at 3 and negative 2. And we're done. Questions on this here? Our solutions. So they did the same thing. We multiplied them together, used long division, got this. Here, that one factors, and we're done. You could have plugged it into the quadratic formula. Questions on this here? Other tests for zeros. You know that the nth degree of a polynomial function can have at most n real zeros. Of course, the nth degree polynomial functions do not have that many zeros. For instance, x squared plus 1 has no real zeros. And f of x equals x cubed plus 1 has 1. So they can have at most the number degree, the degree value, but they don't have to. Now, Descartes' rule of signs. The number of positive real zeros is either equal to the number of variations in the sign of f of x or less than it by an even integer, less than it by 2. The number of negative real zeros of f of x is equal to the number of sign changes of f of negative x or less than it by an even number. And imaginary are the kind of what's left over. For instance, we have this polynomial that is da-da-da. Okay, let's look at an example of this here. Positive, negative, complex. So when I look at the normal function, I am seeing how many times does the sign change from one number to the next, from one term to the next. Looking at this here, so does the sign change from here to here? Here to here. So for positive cases, we could have at most 3. Okay, that's positive. Now negative, we have to take f of negative x. And we're going to plug negative x into each variable, wherever x is. Now a shortcut for this here is if x has an odd, not positive, if the x has a odd degree, the sign changes. If the power of x is even, it stays the same. Because if we multiply a negative number by itself an odd number of times, it's negative. If it's multiplied by an even number of times, it's positive. So 3x cubed, the sign would change. And I can write that out here in a minute. Here, because it's even, it would stay the same. Because it's odd, it would change. We don't do anything to -4. And I'll write that out here in a minute. Now let's see here. Did the sign change from here to here? No. So at most, we're going to have 0 negatives. So here they're all positive. Now how many possible solutions should we have? 3, yes? So if I have 3 positive, 0 negative, I should have how many complex? 0, because I have all 3, yes? Now, it also says an even number less. So I'll pick positive to start with. So we could have 3 at most. So if I subtract 2, we could have 1. Now we said we don't have any negatives because we didn't find any sign changes. So how many solutions do I have between positive and negative for this one? How many should I have? How many am I missing? Yep. And that's it. Questions on this here? We'll re-look back at this one here. I'm going to write this out. So when we plug -1 in, so we're saying 3 times -1 cubed minus 5 times -1 squared plus 6 times -1 minus 4. Negative x, not -1. This would be just negative x. Well, negative x, negative times a negative is a, times a negative is a negative. So negative x cubed is going to be negative x cubed still. Does it still be negative? Well, negative x squared would just be x because it becomes positive. Here we're just going to have minus 6x minus 4 because we don't have any powers for that one. But the first one, when we multiply, we get negative x cubed minus 5x squared. And if you notice the powers that were odd, the sign changes. When the exponent is odd or 1, it changes the sign. And that's it here. Questions on this here? So here it switches. So according to Descartes' rule of sign, there are 3 positive real zeros or 1 positive real zero and no negative real zeros. And that's it. And I will take that chart because that chart's kind of an easier way to do it. If I remember this correctly, it's the missing factors don't really change much. It doesn't, when we're using Descartes' rule of signs, we don't need to add them in. So let's look at this here for positive. So from here to here, did we change signs? There's 1. 4. So we have, so far, positives we can have 4. Now, say we did add that 0x cubed in. Well, from here to here, it would change, yes? Would it change from here to here? So it would change from here to here. But it wouldn't change from here to here, correct? So we still have 4. So adding in times the 0x cubed doesn't change anything. It's not going to actually prove anything. Now we need to do the negative case. So x to the 5th, would the sign change? Yes, because it's odd. So we'd have negative 8x to the 5th. Stay the same because it's even. It would stay the same because it's even. It would change, and then it would stay the same. So from here to here, nope. Yes, no. So how many negatives could we have? 1, because it only changes signs once. So positive, negative, complex. So we said we can have at most 4, and we can have at most. No, we said we can minus 2, yes? Because I would check to see with negatives. If I minus 2 from 1, do I still have a positive number? No, right? 1 minus 2 is negative 1. So if we ever go below 0, because minusing 2, because we can always have that number, positive or negative numbers, minus an even integer, we're always going to minus 2. So I can't minus 2 from 1, so we're done. This is 1. But I can minus 2 from 4, yes? So we could have 2 positives, 1 negative, so that's 3. How many do I need? 2 complex. Well, that's all the iterations because we only have 1 negative, yes? But I could change this down to 0. We'd have 1 negative and that's it. Questions on this here? Now, instead of writing it out and kind of working that through, I just want to look at positive, negatives, complex. So let's say we had 5 and 4. So the degree of this is 9, 5 and 4. Yes, complex always has to have an even number because they always come in pairs. Now, I can subtract 2 from 4, yes? Because I could have 5 positive, 2 negative, and 2 complex. Can I still subtract 2? 0 and... Well, I can do the same thing with positive, subtract 2 and get 3. And I would go back to the top. I'd do 4 again. Because we'd have 3 positive and 4 negatives. And well, I can have 3 positives, 2 negatives, and then how many? 4, yes? And then we could do 3, 2, and not 4, 6. And then, oh yeah, this would be 0. Thank you. Well, I can't move the negatives down any further, can I? Well, no, we can't go below 0. But I can switch 3 to now 4, which is 5. I would need how many? 4. I have 1, 2, and 0, and that's as far as I go because I can't bump positive down any further. So that's how I always work these. I start with the biggest 0 normally, and then do negative down as far as I can. And once I can't, then I bump positive down 1, reset negatives, go back down, and repeat that pattern to find all the possible setups. And this is helpful, especially when looking at a graph. So if I graphed it and I noticed that it doesn't cross the negative side of the x-axis, so I could say here, I could pick out the ones that line up. If I do this here and I find 2 positive numbers and 4 negatives, that means there has to be 1 more positive, because this tells me how many of each I should have. Any questions on this here? Another test is to relate the signs. Synthetic division. We're not going to worry about that, and we are done with 2.5. And this here is the assignment. So a lot of stuff you can use the graphing calculator for to help you find values